I am Costanza Rossi, a postdoctoral researcher at the Italian National Institute for Astrophysics. And I am a geologist, and my research focuses on the geology and tectonics of the icy satellites, and in particular on the Galilean moons, and mostly Europa and mostly Ganymede. So welcome to the icy satellites room, and today we are going to talk about indeed icy satellites, their structural setting, and the mapping approach and technique to investigate their main terrains and their tectonic structures. So if it's not a problem, I switch off my video so you can better hear me. So, yes, okay. So, ice is ubiquitous in the solar system, and it is mostly widespread in the outer solar system where the icy satellites are located. From the Jovian system that includes the main three icy satellites, or better, or also Galilean satellites, thanks to Galileo Galilei that discovered them with his homemade telescope in 1610s, around 1610. And so Galilean satellites, Galilean icy satellites of Jupiter are Europa, Ganymede, and Callisto. Then to the Saturnian system that comprises several icy satellites, such as, for instance, Enceladus, Titan. Titan, that is the unique bodies behind Earth that host liquids at surface. So it is an interesting body in the outer solar system. But also always in the Saturnian system, also, for instance, there are Dione, Thetis, and Iapetus, and other icy satellites. And icy satellites characterized to the Uranian system as well, around which several icy satellites orbit, such as, for instance, Miranda, Ariel, or also Titania, and other icy satellites. So, so such icy satellites are very interesting, obviously, for the scientific point of view, but also for planetary exploration, since they show many similarities to silicate bodies. This is why they are considered as small worlds with a differentiated interior, with an outer icy crust that can undergo to changes in phase due to high pressure. So from the icy crust to a possible high pressure ice mantle, or also a possible rocky mantle. And some of them show evidence for subsurface liquid layers at the subsurface below their icy crust. So such liquid layer, or better, global oceans that occur below such crust makes them as a first-class target for search of habitability in the solar system. Since, as we know, life began on liquid water on Earth, and this is why we are searching for water at a liquid phase, of course, across the solar system. So to find potential possible extraterrestrial forms of life. So the internal ocean of some icy satellites, not all icy satellites show liquid layers below their icy crust, but some of them also show how can I say, they show, for instance, Europa, Ganymede, or Enceladus, they show such oceans, and also other icy secondary icy satellites that are thought to include this internal ocean. Also, for instance, Callisto or Titan. So such ocean represent the main target for the exploration for such bodies, but also even more the icy satellites that show a rocky mantle. So, for instance, Europa or Enceladus as well, they have an internal ocean that is in contact with bedrock that is analogous to what happened on our ocean's floor on Earth, where hydrothermal vents called black smokers are located. And such features have been identified in the deep ocean floor on Earth, and they are near volcanically active places, and they surprisingly host life around their area, and many communities of organisms that live in such extraordinary and extreme environments live there, thanks mostly to the chemicals dissolved in the fluids of the vents. So it is possible that something similar can happen on icy satellites as well. Icy satellites, as I said, those that have the ocean in contact with a rocky mantle, for instance, Enceladus or Europa, where at the ocean floor, it is possible that features similar to hydrothermal vents can heat and enrich the water with compounds that make possible a potential development of primitive life or molecules. But the assumption of black smokers-like features or hydrothermal vents in the ocean floor of the icy satellites is revealed by another very interesting things about icy satellites that is represented by their internal activity. Indeed, icy satellites are geologically active bodies thanks to geodynamic processes that heat their interior and modify their shape. So the main process that affect most of the icy satellites, and mostly the smallest icy satellites, such as, for instance, Europa and Enceladus. So the main process is tidal heating. Tidal heating is produced by gravitational forces between the satellite and the parent planet, which in the case of the Galilean moons is Jupiter. So such gravitational forces induce internal heating and internal heating at the interior of the satellites and lead to variation in shape along the orbit of the satellites around the parent planet. Therefore, the tidal forces, the acting tidal forces, are stronger near the parent planet, so near periapsis, where the satellite is more deformed, than near apoapsis, where it is less deformed, as I said. And another process that usually affects the icy satellites relates to the outer icy crust that can be quite decoupled from the underlying ocean and the underlying mantle. And so it is free to rotate in a non-synchronously manner with the interior. And such process can be induced by many factors, such as, for instance, variation on spin rate, or also reorientation of the tidal axis. And also such process can produce shape changes, variation in shape of the satellite. Another main geodynamic process that affects the icy satellite surface is the icy satellite crust. Is represented by volume expansion of their crust, whose crystallization from the subsurface liquid layer leads to the thickening of the crust, and in turn to their deformation, to their crustal deformation. So I am talking about geodynamic processes that produce deformation, that is mostly deformation of their icy crust, that is mostly deformation of the entire body, but is mostly evidence at their icy crust and mostly at surface. Indeed, the surfaces of many icy satellites, here, for instance, Europa, Ganymede, and Enceladus. Enceladus, that is well known for its taiga stripes that are deformation structures at its south pole. So these three, Europa, Ganymede, and Enceladus, are examples of icy satellites strongly deformed by tectonic activity. So their surfaces show kilometric scale, but also to global scale linear structures that shape them with a very puzzling pattern. So they show a very complex structural pattern. So we can say that from the external observation, it is possible to infer the internal activity. Of course, as many other planetary bodies, also icy satellites. Also, the surfaces of icy satellites are deformed by exogenous patches, mostly originated by cratering impacts, such, for instance, here the example of the surface of Callisto that has been heavily bombarded by impacts. But okay, so come back to tectonic structures. So tectonic structures are the main evidence of the deformation activity of the icy satellites, of the interior of the satellites, icy satellites. And their identification, their mapping, and their structural setting are pivotal to understand the tectonic stress that generate them, also the geodynamic process, and even they support to make inferences about the deep structural setting of subsurface layers and the crust, the icy crust. So tectonic structures are obviously, as I said, important for the geological and structural geology studies, but also for astrobiological implication, since they represent weakness pitches, weakness zones, or rupture paths, or cracks in the crust that act as potential conduits for fluid propagation. So they can help, tectonic structures can support potential feeding of internal potential reservoir, liquid reservoir, and also, most of all, act as connection between the surface environment with internal environment, and possibly also with the internal ocean. So they can be also the link between surface and deep layers. And in this way, they allow an interchange between them. So this means that the ocean is not fully trapped by the icy crust, but some location can be connecting ways with the surface. And obviously, this on the right is a simple example. Instead, we'd assume a fracture network that pervades the crust to possibly its bottom. So the investigation of the surface structures, tectonic structures, allows us to unravel the processes that affect icy satellites and what is concealed at depth, and also their formation, their deformation process. That is strictly, so tectonics activity is strictly related to extensional and strike-slip regimes. So extension is the stretching of the crust that has been identified in all icy satellite surfaces. So these are two of the many examples that we have on Europa and Ganymede, for instance. And these are two models that explain how extension produced the pattern that we observe, the structural pattern of the deformation structures of tectonic structures that we observe at surface. But also, for instance, the example for Europa on the left, such example shows how extensional activity can produce also resurfacing of a newly formed crust from the deep layers. And together with extension, also strike-slip is ubiquitous and dominates the tectonics of icy satellite surfaces. Strike-slip is the horizontal shift and displacement of crustal blocks. Here, such two examples, also in this case, are two of many examples of strike-slip on icy satellites. These are two examples for Europa and Ganymede that show terrains and structures and geologic units that have been displaced by horizontal shift by strike-slip faults. But there are plenty of examples of kinematic indicators for horizontal displacement on icy satellite surfaces. And unfortunately, the icy satellites lack, they show very few evidence for compressional structures. Compression is the contrary of extension, so it's the shortening and thickening of the crust. This is an example of assumption of a model for Europa, for the icy crust of Europa, that suggests a model, a plate tectonic-like model, where compression is accommodated in subduction-like zones that are the compressional zones recognized on Earth. But this is one of the few examples, or the only one, not the only one, but one of the very few examples of pure compression on icy satellites. For instance, on Ganymede, it has not been identified yet compression, poor compressional activity, but we identify a region that has been affected not by pure compression, but transpression, that is a strike-slip with a compressional component. So it is not pure compression, but instead it is called transpression. So strike-slip with compressional component. So the lack of compressional structures on icy satellite surfaces opens to one of the main issues about the tectonics of icy satellites. That is represented by the large amount of extension and strike-slip that requires somewhere else, that requires compensation with a similar amount of compression. But such compression has not been detected yet. So where is the compression on icy satellites crust? This is the main question. So, and also this problem leads to another main issue about tectonics of icy satellites that is linked to the tectonic balancing of their deformation. And therefore, the question is, which model applies for the icy satellite deformation? So on Earth, we have plate tectonics that is not modeled for icy satellites, only for Europa. There is something similar to plate tectonics. But so we have to understand how icy satellite crust compensate and balance their global tectonics. So which model satisfies such balancing, such tectonic balancing. So yes, this is on Earth. Oh yes, sorry. So the plate tectonics that we have on Earth explain the deformation of our crust. So that is characterized by, maybe you already saw something similar yesterday in the presentation of yesterday, but so the deformation of our crust is characterized by at top by a rigid, brittle outer shell that is subdivided and then fractured into plates that drift on a warm convective mantle. And where such plates meet, their motion, their relative motion determines the type of the plate boundary that is represented by long lineaments or folds that can be convergent boundaries, so characterized by compressional structures, but also divergent boundaries characterized by extensional structures or strike slip boundaries. And the displacement of the tectonic plates shows a mechanism that is balanced, where the lost surface through shortening in convergent boundaries is balanced by the formation of new crust from divergent boundaries. So on icy satellites, we still have no models, as I said, to explain the global mechanisms of their deformation of their surface. A model similar, as I said, to plate tectonics has been proposed for the icy crust of Europa, but still it can explain the other icy satellites tectonics, for instance, for Ganymede and also Enceladus. Yes, as I already said, we have to understand how icy satellites crust compensate their global tectonics and which model satisfies such balancing. And for sure, the evidence of only extension and strike slip structures and the lack or compression structures are not helpful factors, and such factors don't allow to fully understand their tectonics, and so their icy crust deformation. So the investigations that focus on such issues are based obviously on remote sensing analysis, but for most icy satellites, the data are unfortunately not quite optimal for global mapping, since we still lack complete global imaging coverage at a resolution that can be sufficient to distinguish tectonic structures and terrains. But conversely, some satellites have been also well observed by past missions that acquire good coverage of image data. So the past missions that explore the outer solar system, it started with Pioneer, but later some of them focused particularly on the icy satellites. So such missions have acquired the data that we currently investigate today, of course. And so after Pioneer, mainly both Voyager probes that have been launched in 1977. And then more than 10 years later, Galileo probe has been launched in 1989. And then subsequently, in 1997, Cassini probe has been launched. So such missions provided us data that we still use and still allow to produce science. For geological investigation, mostly for mapping purposes, the cameras of such missions acquire data from the Jovian icy satellites, and mostly are Voyager and Galileo missions. The images of Voyager have regional scale resolution that allows us to cover all the surface of the Galilean moons, so mostly Europa and Ganymede, and also Callisto. While the data from Galileo mission, they have higher resolution, that can reach local scale areas at less than 10 meters per pixel, so very high resolution. But such data represent images on spot areas, so very few areas on the surface of such satellites. It allows us to such data allows us to perform global mosaics of Europa and Ganymede based on mostly on Voyager images and Galileo images that cover some spots on such mosaics. And for the Saturnian system, the Cassini mission performed an excellent work by taking regional and local scale resolution data that allow to produce global scale mosaics, for instance, of Enceladus. And currently, there are other missions that are focused on other targets, of course, such New Horizons that has been launched on 2006 to Pluto, focused to Pluto. And also Juno missions that has been launched on 2011 to Jupiter, but they acquired few images at very low resolution of the icy satellites, some icy satellites that have been mostly useful, for instance, for eruptions of Io, that is the first Galilean, which is very volcanically active body, but it's not an icy satellite. And the exploration of the icy satellites continues, and being a first-class target for planetary exploration, it will be among the main programs of space agencies for the next decades. So last year has been launched JUICE, finally, that will arrive at the end of this decade on the Jovian system. And JUICE will mostly investigate Ganymede. We'll observe at high resolution Ganymede with a global coverage. And I would like to remind you that this afternoon there is a seminar by Alice Lucchetti about the JUICE mission that will provide you more knowledge about JUICE mission. And additionally, this year will be finally launched also Europa Clipper. Europa Clipper is planned to investigate mostly Europa, of course, investigate Europa at high resolution with a global data coverage too. So both Such missions will provide us data that will be used to produce new global mosaics, for instance, and we are waiting for the data, the geological implications that will be inferred. So it is optimal to have updated and high-resolution data to perform multi-scale analysis, so integrate the future data with what we already have from Voyager and Galileo data, but this is more from many points of view, for many topics, and in particular for the geological investigation, to understand also changes in geology, variations in geology and structural setting, for instance. So mapping is a powerful tool that requires updates to understand multi-temporal and multi-scale variation in geology, geological variations. And moreover, the mapping work of the past missions allow to select optimal areas as target for higher resolution observation of future missions. And generally also not only for the camera, but also for other instrument activities such as investigation of the ground penetrating radar, that you will get more knowledge from another seminar of this afternoon by Barbara Cusciotti. So the data, you can find the data of the icy satellites of the past and current missions online. Already, I think that Riccardo already mentioned on Monday such websites that are the Planetary Data System, that is an archive of digital data products from planetary mission, NASA planetary missions. This archive is managed by planetary scientists to support the worldwide planetary science community. And another website where you can find data of icy satellites is, for instance, the pilot website, Planetary Image Locator Tool. That is a web-based search interface that allows to select the data on areas that we need to investigate in an interactive manner. And also there is Astropedia in the USGS astrogeology website. That is a portal and catalog of mostly cartographic products. And for instance, here you can find the global mosaics of the main icy satellites, for instance, Europa and Ganymede, and also their geologic maps and their GIS data sets. So this is very useful. And another interactive portal that you already saw is the Solar System Track that allows you to better visualize and also explore and analyze the surfaces of planetary bodies, and of course also icy satellites using data returned from planetary missions. And the data of icy satellites, the acquired data of icy satellites require a processing that is very meticulous and detailed. So unfortunately, we haven't always and everywhere optimal data, but thankfully we obtain anyhow good data to proceed the geological investigation of icy satellite surfaces. The main tool to process image data of the icy satellites is ISIS. That is an open source software that you can find online and download on GitHub. And it is important, it is fundamental for the processing of raw data into products that are ready to investigation. It includes tools to process images such as contrast, stretch, image algebra, noise removal, filters, statistical analysis, and so on, and so on. And so additionally, also ISIS allows to georeference the data in the correct cartographic location. So this is also very important. So another open source tool is the AIM stereo pipeline that mostly allows to process data to produce cartographic and geodetic products, including the production of digital terrain models through stereophotogrammetry techniques, and the production of DTM is very useful for the knowledge of the topography of the icy satellites, but in general for planetary bodies. It is very important to understand the third dimension of what we observe at surface. But unfortunately, we are talking about icy satellites, so this is not an easy technique with the data of icy satellite surface. And unfortunately, only some data allow the stereophotograph, such technique that is used in conjunction with two images taken from two different positions of the same areas to produce a three-dimensional image. There is also another technique called shape from shading that allows us to produce DTM, digital terrain models, from a single image according to lighting condition, but we will still keep focus on mapping purpose.